right. By the way, let me point out there's special events coming up, quite a few of them. B-Sides this weekend, and Hack the Bay coming up on Monday, and then RSA all next week. And you can get into the expo for free if you Google for a free expo pass. And you can get into all the stuff on Thursday, the free college day, by signing up in advance with your EDU email address. That's what I'm going to do. I'll be there on Thursday. So I recommend going to these things. They're all good for you, and they're all worth extra credit. Just let me know if you go to any of them. All right. I just mentioned I'm avoiding B-Sides because I got COVID there twice. It's in a movie theater, and movie theaters don't have good ventilation. So that's one reason why I'm going to avoid this one. But if you're not afraid of COVID, you can go to that one, and you might be able to stick to the more ventilated areas and be all right. But the trainings were in little movie theaters, and I'm pretty sure I got COVID there. Anyway, these other ones, though, RSA is very well ventilated, and as I remember, Hack the Bay was too. Well, these seem safe enough to go to. All right. Anyway, so let's move to the official material, which is here. Today is elliptic curve cryptography. Hey there. You in this class? Okay. What you looking for?
I'm going to speak to you after class.
Okay.
When are you done?
What's that?
I'm going to speak to you after class. When are you done?
7:30.
7:30.
Okay, good. All right, good. Okay, good. Anyway, so, all right, we're down to elliptic curve cryptography, which I moved later in the class, realizing it'll be less prominent and not every student is going to do it because it's not so important. I mean, elliptic curves used to be the most important public key cryptography because RSA is old-fashioned and inefficient and has a lot of problems, and elliptic curve is basically what replaced it. It was the standard for a long time. The problem is it's vulnerable to attacks by quantum computers, so it's on the way out just like RSA. I will talk about it, but I'm not going to push it as much as I used to because we really got to be moving to the post-quantum algorithms, of which we got several projects up now, and those are the ones. That's why I thought the quantum computing is probably something to cover earlier. This shows you what the modern algorithms, which we've demonstrated previously. So let's talk about elliptic curves. It's chapter 12. I got to bring it up here. All right. It's very nice mathematics, like RSA, and it did protect all of us for a few decades, but everyone's moving away from it now because of the fear of quantum computers. All right, so we'll talk about what they are and the important features of them, the various weaknesses they have, and then so on. So elliptic curves were introduced in '85, and they're much more efficient than RSA because it's a much shorter key. An elliptic curve with a 256-bit key is stronger than RSA with a 4096-bit key. So it saves you a lot of computer time to use elliptic curve cryptography. In practice, it seems to be about 10 times cheaper to secure your server with ECC-based certificates. So OpenSSL added it in 2005. These guys added it in 2011, because just like every chapter in this book I've talked about, it's the new system. It was better, but the old system, RSA, was working well enough, and it was the standard. Everybody had the code written and hardware deployed, and so people stick with the existing things until there's really a reason to move to the new one. Bitcoin came in later and was used in elliptic curve cryptography. And like I say, anything based on the discrete logarithm problem could use ECC instead. All right, anyway, so an elliptic curve looks like this. Y squared is x cubed plus ax plus b. So depending on a and b, you get different curves. Here's one possible curve. You have a sort of egg-shaped thing here and a sort of hyperbola-looking thing there. That's what it is. It's symmetric across the y-axis, because this calculation gives you y squared, so there's a negative and a positive value that have the same value of y squared, so it's symmetric about the x-axis. Now, this is the elliptic curve over real numbers, which is not what you use in cryptography. We don't want floating point real numbers. We want integers in a ring, sort of. We want a group of numbers, because remember, the general thing is if you encrypt something that's like 10 bytes long, you want the encrypted version to still be 10 bytes long, something like that. You don't want it to get a lot longer. So you want a closed ring where there's certain values, and you're just going to shuffle to other values in the same set. So this is elliptic curve over integers. So you have a modulus. This one's 191, and so the group of Z191 goes from 0 up to 190, and so there are 190 points with x and y here. And so that creates a field. And we talked about this before. This is the mathematical object you need for public key cryptography. According to this system, all of these are essentially equal to the discrete logarithm problem. You have addition and multiplication, which you define. You need an additive identity element, which is 0. And you want inverses for addition, which for an element x, it would be minus x. And the inverse for multiplication would be 1 over x. You could write it that way. So if you have a group that has all these properties, where you have addition and multiplication, you have an additive and a multiplicative identity, and you have inverses. I'm not sure about the multiplicative identity, but anyway, you have inverses. That's called a field, and if you have a finite number of elements, it's called a finite field, and that's what we want. So now you just have to define how it works for elliptic curve cryptography. And so here's how it works. If you have a point P and a point Q, then the way you find the sum is you draw a line connecting them and find the point where it intersects with the curve and reflect around the x-axis. So if you have point P here and the point Q there, you draw the line, you find the intersection, and flip it about the x-axis. This is where P plus Q is. This is a strange operation, but remember, it doesn't have to resemble addition. It just has to be some way to combine two members of the group to get another member of the group. And you can call it addition. It just has to have certain formal properties, and it'll work for encryption. So P plus minus P, the negative point is to flip it about the y-axis. So if you do that, P and minus P, you get a vertical line. So if you extend that line, it will never intersect anywhere, and so it goes to the point at infinity. And in any direction, an infinite distance out, you call that one point at infinity, and that's what passes for 0 in elliptic curve cryptography. So it's a little mind-bending, but remember, it's just the formal structure of these operations that matter. It's not that it resembles our intuitive idea of what addition and multiplication are. And so if you want to take P plus P, the same point twice, then you make the tangent line, see where it intersects, and go down to the opposite on reflecting around the x-axis, and there's another way to create something you call P plus P. So now you can do multiplication. K times P, you could do P plus P plus P plus P, and you can make it faster by calculating P2 is P plus P, and P4 is P2 plus P2, and P8 is P4 plus P4. So just like we did with exponentiation for RSA, this way you can calculate even a large multiple of P without having to do too many calculations. You really have to do only about the log of this large number worth of calculations. All right, so a group is a series of elements. Examples are X, Y, and Z. Each one of these is a point in the elliptic curve, and we'll have an operation. So closure says if you combine any two of the groups and multiply them, the multiplication is still in the group. You can do the multiplication in this order or in that order, and you'll get the same answer. There is an identity element. So if you multiply by the identity element, like 1, you get the same number. And there's an inverse. For every x, there is an inverse. So x times the inverse will give you the identity element. So P, Q, and R, an addition, form a group. If P and Q are in the group, P plus Q is also. P plus Q plus R is the same as P plus Q plus R. The identity element is the point at infinity, so P plus the point at infinity is still P. In the inverse, xy and x minus y, if you add them together, you'll get 0, the point at infinity, like we showed. So this is, you have all the mathematical properties you need. It's just a little strange. And so here's the discrete logarithm problem with elliptic curves. Given P and Q, find K so that Q is K times P. And this is effectively a logarithm. This turns out to be a very difficult problem. All right. So if you do it with smaller numbers just to see how it works, you can figure out how long it is. If the P is the size of the group and it's n bits long, the security is n over 2 bits. So 256 bits of P will give you 128 bits of security. All right. And therefore, it's much faster. The math is much faster because you're using smaller numbers than RSA. So you can now use this to do Diffie-Hellman key agreement, which looks very much like before. Now remember, this is what RSA key agreement was. You pick an A, a random A, this person picks a random B, and they transmit G. G is a publicly known number, G to the A, and this person sends G to the B, you now take G to the B that came from that person to A, you get G to the AB. This person takes G to the B, multiplies it, takes it to the power A. You've now agreed on a shared secret, but the stuff you sent over the wire is not easily reversed to determine A or B, because that would involve factoring numbers into their prime components, or solving the discrete logarithm problem, all related problems. And so it's the same with elliptic curve Diffie-Hellman. You choose a fixed point G, and now you multiply G times your secret and transmit that. This person multiplies G times their secret and transmits that, and now you multiply your secret times the number that came over the wire, and you have created a shared secret. You both agreed on it, and again, the problem you sent over the wire could only be reduced to uncover your secrets if they could solve the discrete logarithm problem, which is a hard problem. So it's just as good as any of these. All these are mathematically very similar, and like I say, that means they're all on the way out because they're all going to be broken by quantum computers. So you can sign with elliptic curves just like you can sign with RSA, and this is what Bitcoin uses. You've got a signature generation and a signature verification algorithm. So to sign it, you have a private key, and people know the public key is that multiply, that times a generator, and you have to know which curve to use and how many points there are, and the coordinates of a base point. The G is public. And then, so signer hashes the message, like a SHA hash or something. Then you pick a random number K and calculate KG, and your signature is constructed this way from the X and Y values of the KG. These are operations you can do with the secret, and they can be verified at the other end. So the signature is much smaller than other. So if you're using 256-bit numbers, RNS are 256 bits long, and the signature is 512 bits long, so that's not too bad. And RSA gives you encryption and signatures. It was the original one much earlier, and these days they've improved their cryptographic standards, and so when they developed ECC, they included other things like key agreement and things like identity-based encryption. It's a more full suite of functions. That's why pretty much everybody's moved away from RSA to elliptic curve signatures, and those are approved up through 2030 by the government. But around 2030, they say we really all got to be switching to quantum proof algorithms, because everyone doesn't expect those quantum computers to be a real threat for at least another 10 or 20 years. So we have a little bit of time to do the transition. All right. And like I say, they're simpler and much faster. By the way, RSA verification is sometimes faster if you use a small public key, but in practice, you see here, signing with RSA takes 7 milliseconds, but with elliptic curve, it takes much less, an unmeasurably small number here. To verify it takes about the same time, 1/10 of a millisecond in both cases. To sign, how many things can you sign per second? You can sign 100 per second RSA, but you can sign 21,000 with elliptic curve in the same time. And to verify, it's about the same. So, that's why I say it's a whole lot cheaper, a whole lot less CPU time is used to protect your data with elliptic curve cryptography than with RSA. So you can encrypt with elliptic curves, but this is rarely done because your key is only 256-bit long. The message can't be much longer. It can only be about 100 bits. So that's a problem. So what you do is you don't encrypt a message with elliptic curve cryptography. What you do is you do that Diffie-Hellman thing to create a shared secret. We talk about here, you didn't send any message here. You just sent a couple of random numbers essentially, but now you've agreed on a shared secret. So now you run that shared secret through a key derivation function, which is just a hash function with possibly a salt and such. And then you get an AES key, and then you encrypt your data with AES. That's what you do. All you really need is to get a shared secret at the other end. With public key cryptography, you can use private key cryptography after that. And remember, AES is not at danger from quantum computing. All we'll have to do to survive quantum computers with AES is move from 128 bits to 256. And that algorithm already exists. It's been a standard for a long time. So we already have an algorithm that's perfectly fine. We don't have to have a new one for a world with quantum computers for private key computing. All right. So that's the technique. And so you pick a random number D, commute the point Q, and then you have an ephemeral key pair and you compute a shared secret, and then you use a key derivation scheme to make a symmetric key for AES, and then you encrypt everything with AES and send it off, and you're ready to go. And we've done all that in the projects. So now you have to choose your elliptic curve. Remember, A and B are these parameters. You have to somehow choose what are good values of these. You have to choose an order, which is the modulus, and you also have to choose A and B. So the order, it turns out, must not be the product of small numbers, or it may be crackable. So it's best if you can do addition of P plus Q and P plus T without having to have a separate algorithm for that. That makes it, because otherwise your separate algorithm might lead to a timing difference or some other difference that can be exploited to learn information. So it would be considered better if you can use the same algorithm for both of these operations. That's called unified addition. And when you choose A and B, the person who recommends them should explain how they derived A and B, so you can allay suspicions that maybe you chose an A and B that's got some kind of backdoor in it. So the National Institute of Standards in 2000 specified 5 prime curves. They recommend the modulus is a prime number. These are the most commonly used ones. There are 10 others that exist but are rarely used. And so the most common one is P256. The prime number is this number, 2 to the 256 minus 2 to the 224 plus these numbers. So this is, there's a whole lot of people that make these prime numbers that are related to a power of 2. It's apparently pretty easy to generate them mathematically. And so this thing is a prime number, and it's pretty easy to write down in this form. So that's the modulus. And your A and B are 3 and B. So A is 3, and B is a 256-bit number. And B is the SHA-1 hash of this thing. But the NSA never explained how they got a B. And this is worrying, because they have in the past recommended cryptographic systems that they have a secret backdoor into. So people wonder. Now, most experts don't think there's a backdoor, but Bruce Schneier, a very famous cryptographer, says few people trust the NIST because of Snowden. Snowden revealed that NIST was poisoning our cryptography, and Bruce Schneier wrote, "I no longer trust the constants. I believe the NSA has manipulated them. I looked at random seed values, and no justification is given for this B value. I now personally consider this to be smoking evidence that the parameters are cooked." And so Bitcoin Tor and many applications avoid the NIST-derived curves and instead use public curves that are not approved by NIST. So this is a sad thing, but that's where we've been at for decades. The National Institute of Standards was in fact recommending broken cryptography so they could spy on us. And that means it's not safe to use their stuff, especially since they've many times demonstrated that they can't keep their secrets. Stuff is leaking out of there. So if they have a back door and they can't keep the secret, then other people will find the back door, and you really don't want to use those algorithms. So there are alternatives. Here's one that is not from NIST, 25519. And it's faster, uses shorter keys, and doesn't have any suspicious constants, and it has that additive property you like. So this is a popular one. And so A is this number, and B is 1, and the prime number is 2 to the 255 minus 19. So this is used all over the place. A lot of people use it. They don't use the NIST standard very much. They use this one, which is understood, and everybody feels like they can be confident there's no backdoor in this one. There's another one called 256K1, another one here, used in Bitcoin, just another public curve. And there are a lot of other ones. There's old national standards from other nations. There's a bunch of them. There's newer curves that people have developed, supposedly more secure, that still aren't used very much because the curve 25519 is good enough. But there are a bunch of others. If we ever find some reason why these aren't good enough, there are plenty of others that are contenders. All right. So things can go wrong. Elliptic curves have more parameters, so there's more opportunity for mistakes in your coding. The math is a little more complicated. And of course, that means you might have vulnerability to things like side channel attacks, like timing attacks, or power consumption attacks. When you write this complicated code, you may introduce those vulnerabilities. When you sign, you need to put in a random number in your signature, and if you reuse the number, then the attacker can find it. So this happened to the PlayStation in 2010, and this is an issue. This happens in all cryptography. When they have a random, a lot of them have this notch, a number you can only use once. If you break that rule and use it more than once, often you ruin your cryptography, so that's another mistake you can make. And then there's the invalid curve attack I mentioned in the news section. This is pretty awesome. You remember there were some curves that are weak because of bad choices of the parameters. And so what you could do when you're trying to do this negotiation, you don't know the random secret, but you transmit a malicious point that is in fact on a weak curve. And if the person at the other end does not check to make sure that the point is really on the right curve, they will multiply it by their secret and send it back. And you can now find the secret because you sent them a point on a curve that can be reversed. This is called the invalid curve attack. And it's just, again, it's a failure to implement it correctly. You got a point. Remember that when you send a point over here to engage in a Diffie-Hellman, this point is supposed to be on your curve you're using. But if I send it on a different curve and I don't check for that, I might leak it out. So it's another sort of mistake that people made. And that's the invalid curve attack. And that affected a whole lot of libraries in 2015. So, you know, that's the thing. When you have a complicated thing with a lot of parameters, there are a lot of ways developers can make mistakes. So that's, that happens. All right. So let's take a look at the cahoots for this stuff. All right. Oh, I gotta adjust it so you can see the last digit. It's 53 it ends with. There you go. Good. Oh, okay, good. We got 3. That's nice. We'll carry on. All right, so how long should an elliptic curve key be? $256 is enough for good security. RSA, you need 4096. 64 wouldn't be enough for anything. You can crack that by brute force. So 256 bits is what's recommended. All right. How long of a message can you encrypt with AES? Any length, right? You can, if you're using the old system like cipher block chaining, you can have as many blocks of 16 bytes as you want. If you're using the modern system of Galois counter mode, it acts like a stream cipher. You can just encrypt any message of any length. It doesn't even have to be multiple of 16 bits. That's the point. This private key encryption is wonderful. You can send as much data as you want with it. All right. All right, which curve is suspected of having NSA backdoor? P256 is the official approved curve which a lot of people refuse to use. All right, and how long a message can you encrypt with elliptic curve? I think this means integrated encryption scheme, I'm not quite sure, but anyway. I was afraid of that. Okay, the elliptic curve itself can only move 100 bits, but the integrated encryption scheme is the one that creates an AES key and uses that, so again, it's any length. Good, you people got the right answer, although I wasn't sure I was gonna. All right, so anyway, there's not much competition today anyway. I think there's only 3 of you, so you're all gonna win.